So hello, good morning, everyone and everybody. Here, very happy to be here, actually, this interesting event, and thankful for the organizers of this dev room. My name is Guilherme, and I'm representing here the Qucs, Quite Universal Circuit Simulator, and I will give you an overview where the project's coming from, what we are doing now, and where we hope to be in a couple of years. So the project was created in 2003 by two German engineers in TU Berlin. They left the project about 4 years ago, but then in this period that they were active up to today, we have roughly 20 contributors. The main interface was translated to 20 languages. It's cross-platform, so it's mainly developed in Linux and Mac. However, we have a big slice of users on the Windows. To give you an idea, on the last release that we did, in the last 6 months, we got 43,000 downloads from the binary package on SourceForge. And if you look at the download history on SourceForge for the project history, it's kind of steadily increasing. Roughly when they left, there is a drop, and then it picked up 2 years ago again. And our main users are school kids, actually, learning circuits. But we also have research done on this package. We have hobbyists like RF people and guys developing RF circuits. And we also have professionals doing things like signal integrity and using the advanced features that we have on this package. So what we have inside there? So it's basically a schematic capture. We have our own simulator. It's called Qucs. We have other packages. One that joined early on the flow was ASCO, which is a circuit optimizer. Then we have some simple hookups for Icarus Verilog and FreeHDL. It has built-in data visualization, has an equation system for pre-processing and post-processing on the schematic. We have a nice component library, and we also have tools for design and synthesis. It's extensible because we can import spice, some flavors, and some constructs, not everything. We have an ongoing development for increased Verilog A capabilities, and it also has some mostly post-processing and an experimental feature for doing the transient solution with Octave and MATLAB. Basically, it's a C++ project. We use Qt for the user interface. We are still struggling with Qt3 support on the graphics. We are porting now for Qt4. You can build it with traditional auto tools or CMake. Use gperf for hashing, Flex and Bison for parser and lexer. We also make heavy use of ADMS. We're going to see later also that's related to the Verilog A conversion of models. And most of the documentation at this moment is written in LaTeX or PDFs in the end. Where can you find us? So we have the website. At the moment, we have roughly 10 people actively working. The last month, perhaps 5 people committed to the code base, but it's getting more and more people. We have sort of extensive documentation. We have online help. We have these workbooks. It's roughly 200 pages each with tutorials, reports on how the things were implemented, and also a technical manual with not really related to the implementation, but more like textbook-like instructions. We had originally SourceForge. Then we migrated to the Git repository. We still use the tracker in there, the forum and the mailing lists, but we are moving heavily to GitHub. We are activating there the issue tracker, the wiki. We also have continuous integration with Travis, building on Linux for GCC and Clang, and for OS X also. We are doing coverage on the simulator. Right now we have 40% coverage that we are trying to automate the testing so we don't break stuff as we develop. And yeah. And again, the tools. For graphical tools, we have the main schematic capture, which is called Qucs. There is a recent addition that's used for creating active filters like audio amplifiers and things like this. There is a small tool for creating attenuators. There is a simple edit test editor, a tool for passive filters, the help I told you, a simple dialog for matching networks, a library of components. There is this simple one, REST codes for calculating resistor colors and the value, the commercial value. It's a simple one, but it's nice. And there is a transcalc that's for transmission line calculations. In total, we have roughly 180 primitives, components that you can use for this simulation that I'm going to show later on. And for command line tools, we have the main interface has a beginning of command line interface that you can convert schematics to netlists. You can export printout of the schematics from the command line. Then you have the simulator and the converter that converts back and forth between different netlists and data formats that we use. And as I mentioned, we rely on other packages like the optimizer, the Verilog A translator, iVerilog, FreeHDL for VHDL, then PSpice to Spice, Octave, and I am at least increasingly using more Python. So these slides are for backup. I'll try to make it live so it gets more. If you have questions, please stop me and I can try to answer your questions. So this is the main interface. Here we have project manager. You have the contents of each project. You have the components like lumped sources, transmission lines for RF people, and we have these Verilog A devices, and you can drop in diagrams, and you also have libraries of where the primitive components people took from the datasheet, the parameters, and put in there, so it's easier to use. And the subtools we have here, for instance, the text editor that can be inside or outside of the tool, the filter synthesis, which is launching on the background. You can calculate, and you can paste it here. And what else? This for the line calculation. Then you have the component library that can be also outside. So you have here the list of components. But I skipped something. So this is for transmission line calculations. You have a handful of transmission lines that you can put the parameters, you can synthesize, and then you can, this is a simple one. But you could have also Qucs, synthesize, and so on. Let me close this. Close it. So you have simple passive attenuator networks also that you can give the input and output impedances and so on. And you calculate, and you got the idea. What else do we have here? So then this is the resistor. It is not working now. So it is. So basically put 45 and then it creates the 47 for you. I can put the colors here. It's nice for students. And okay, this is more or less the interface. Then I will show you some examples. Here is the schematic. So this is a simple one. It's a RLC. The R is given as a parameter from an equation. So it's a pre-processed value. These equations can be quite complicated. And if you simulate, so it's simulated, give you some report, and here is the response. However, you can also do like this. You can deactivate that, activate that, and then we are now sweeping the R value in 5 steps, and there you go. So it's nice that you can kind of interact and play a bit with the circuit. And this is the first one. And let's move for a second. This is a quite nice model for a 555 IC. What's different here is that it's not a SPICE. It's actually a macro model. It's sort of a system level simulation. So Mike Brinston did it quite a while ago. You can pop in and you can see the blocks, sort of macro modeling technique. Then you can go inside and you can go outside. And you can see that we have also some support for digital components like an OR gate. Then you can make interesting experimentation with that. And then you can simulate. So it's a transient simulation. and this is the response. So it starts up, then you have the internal signals, and this is the output, the clock that's generated from the 555. So you can have, as I showed before, the graphics together with the schematic, like here. Oops. Like here. And or you can choose to put it aside and document it nicely and tidy. This is an example with the optimizer. So let's say I went for the textbook, I got equations for this bandpass filter. I did the rough calculation. Okay, it looks okay, but maybe I want to see if I can improve based on equations. Like I want to minimize the side lobes, reduce the ripple on the pass band, so we can create an optimization box based on these equations, and the optimizer is going to calculate for us the best parameters given the constraints that we gave. So it's now simulated. It's using ASCII in the background. It has a generic genetic algorithm for finding, the best parameters on these metrics. So it's running, and it's done. And then this is the final circuit, and then you can find back the final parameters inside of the simulation box. Qucs was initially developed as a RF simulation tools, and there is a strong background on frequency domain simulations. This is, for instance, a 5-stage microstrip filter, which use coupled microstrips. In this case, it's quite tiny microstrips, like 400 micrometers wide, 5 millimeters long, and ½ millimeter separation. And then this person, it was a previous contributor, developed this filter. Then you can have a substrate, and kind of interesting. Again, the equations, and it simulates. Well, let's see. I can plot here the Smith chart, the 1, 2 here. Okay, it's a bit coarse, but then we can increase the data points here. Give you a sense of, it's quite fast. Okay. And then there you go, it's a bit nicer now. And there is plenty of other transmission lines here that you can play with. And okay, these are were my, so to say, basic examples. Just fast forward here. I forgot active filter. Tools, which is not in this version, is for the next version, so I will show you later. And my backup slides. Recap. This is a new filter actually for the next version. There is more things. So these were about the command lines that I forgot to mention. The simulator can do DC, transient, AC, AC with noise, S parameters with noise. And the harmonic balance, it works, but it has some issues. We are working on that. Qucs uses a different netlist. It's their own netlist, our own netlist, our own data file. And there is this converter that we use to move from SPICE to Qucs and to create libraries from SPICE components. And there is other exports from our data to CSV. It can read and can deal with touchstone, for instance, for S parameters. You can pick up from the machine and plug in there to simulate. And these were the 5. I forgot the Verilog example. So I gave you these 4 examples. And we have also, it's a simple one, but anyway. So it's basically a test bench for a Verilog counter. So this is the Verilog component. It helps you to create this symbol. And basically, it's a counter. Maybe let's put 4 bits here. Then we save. Then we pop out. And then we simulate. And it kicks off. And it's already solved. So it's called Icarus in the background. And here you have the counter. 1, 2, 3, and wrap around. Okay, this is a simple example, but it's nice to have for students mainly. And perhaps in the future we can think of having analog and digital simulators, co-simulation, which it's quite nice. So back to my slides. And now I'm going to show you 2 features that are in development, which is the Verilog A model builder and the ngSpice or Zeiss front ends. which are, let me just fast forward. So why is Verilog A important for us? Because we have several models that are written in Verilog A. We have at the moment 53 models, and many of the industry standard models, compact models for semiconductors or transistors, they are based on these models, and many of them are written in Verilog A. Vladek's going to speak about this later also, and we have, to translate Verilog A into our C++ code, we use this tool, which is ADMS, which it's basically a code-to-code translator. It has, you give the Verilog A, we give a set of transformations, and it spits out code. I say code because it can be anything, even documentation, text. It's a quite interesting tool. The limitations is that at the moment we have just a subset of the Verilog A standard, Verilog AMS standard, and Qucs at the moment has no support for this kind of voltage or nodal contributions. It's just flow or current contributions. Anyway, let me close this one. Now I go for the development mode. Yes. So this is a version that has a more advanced feature related to the Verilog A. So for instance, this is the BSIM 6. I think we are the first open source project that has some support for this. It's about 4,000 lines of Verilog A code, and you can, if you want to have a look at it. And basically how it works, we can create a symbol for the model. So it extracts that. When you save it, it parses the parameters and stores the parameters on the component for you. Then we have to build it. So now it's kicking off ADMS and the CC compiler on the back, C++ compiler in the background, so it is spinning. So this 4,000 lines of Verilog A yields some 40,000 lines of C++. Here is the report of the Verilog A compiler, and here is the C++ compiler with some warnings. But the model is built as a shared library, and it's loaded on the core solver during simulation. So this is done. And what I'm going to simulate now is a chain of, I have to load the components because they're dynamic. And I also have to load here the model card, which is the parameters from the manufacturer, so to say. So we don't have yet the include option on the core, so we have to do it manually. But now it's, so to say, configured. Then we can now load. So it's this inverter that we are going to simulate. Actually, it's a chain of inverters. It's our five-stage inverters. And I'm just increase a bit the runtime so you see that I'm not cheating here. And it's kind of slowish, but it works. And it works quite well because the results are matching the HSPI simulator, which is the simulator that the people from Berkeley that developed the model used to sign off the model. So we are quite happy. There you go. So you have this sinusoidal input, and then it becomes a rectangular pulse. And that's for it for the Verilog A. So it's quite interesting. I think we are the only tool that has this sort of interactive way of building Verilog A and loading Verilog A compact models. And let's close this, and then I will switch to the ngSpice and Zeiss. So this is because we have some limitations on the transient solver of Qucs, and we have high quality open source simulator engines out there. And then this fellow from Russia, Vadim, it's making it work in a way that we translate the Qucs netlist to this, targeting these specific simulators. And this is more or less how it looks at the moment. So we have here this audio amplifier, which doesn't work with the current Qucs. And we are running an AC simulation and transient simulation. We are putting 1 voltage input, and let's see what we get on the output. Then we have here simulate with Spice at the moment. We can run ngSpice first, and that's it. Cool. And then we can run Zeiss serial. I only have the serial. This is a Sandia Labs solver. If you happen to have a cluster, for instance, you can run MPI with this thing. So quite powerful, heavy guns here. So let's run and run. Great. Then let's go for the results. Yeah, this one. All right. On top, we have the AC response. So we put 1 volt, and we are getting what? Yeah, roughly 13 gain on this amplifier. It's quite flat between the 20K hertz. Quite nice. Here is again the transient response. Nice. ngSpice and Zeiss are in agreement, and hopefully we can bring Qucs in agreement with those simulators as well. So this was it for the demo. So let's switch back a bit back to the project again. This is the current status. So on the graphical interface, we are struggling a bit to finalize this port and go entirely on Qt4. And it's difficult because we have basically to redo the graphics. It's going to work, but it's going to take time because we're a small team. We are doing at the same time quite a lot of refactoring, bug fixing, and small improvements that don't break the tool. And yeah, and we are doing also some refactoring and porting some custom code to the C++, C++11 library. We are porting our LaTeX documentation to a Sphinx-based documentation to ease the contribution on this side. We are also starting to push a translation platform for the Qucs GUI and the documentation. And these developments that are more prominent now, there's also this last one that's quite new. It's a new tool for modeling devices from Berkeley that it's based on Octave or MATLAB, and we can use that with Qucs. And the roadmap is actually bigger than that, but it's just a few highlights that at least I would like to see happening. So we have already a simple GUI and a simulator, and we are doing refactoring and yeah, moving forward with make it better, hopefully. But we still lack some powerful design analysis tools, like nice algorithms. I would like to have an API, perhaps interface with Python or Octave. In both levels, the simulator and the user interface. The harmonic balance works, but it needs a bit of addition. There are other simulations. I was also in contact with the creators of OpenEMS and NEC2++ to see if we can get some sort of electromagnetic simulation tied to our, tie into the workflow the same way we did with ASCO and Verilog and VHDL. We are working on bringing more compatibility with SPICE flavors like Spectre and other commercial simulators. This is a big thing for me, at least. I would like to see co-simulation. Maybe I can talk with the Verilog and VHDL guys to see if we can set up a DPI or other sort of interface there for achieving that. We need some more compact storage and faster storage, like H5. There are other standards of models out there that we'd like to offer. And ultimately, we'd like to have a smooth way to produce what we simulate and design. So perhaps a tighter integration with a PCB or layout tools out there, maybe KiCad or KLayout. More on the technical side, have some more advanced Monte Carlo based on technology files to give a further push to the quality of the simulation. And ultimately, lab automation are to fetch data from equipment, do some optimization, and things like this. So these are I will just leave for background. I can show you I have time? Yeah. Quickly, the page. So this is the page. It's simple. We are still working on it. You can find documentation here, for instance. These are the tutorials I mentioned. The 555 is here. There's a workbook. There is also a Russian translation of the workbook, some reports, and some other reports. And then there is also the technical manual here. This is our organization on GitHub, where we store our stuff. We also have, I think, the most up-to-date version of the Verilog A converter is our version, which is released. Actually, I released that version as being the latest one on SourceForge. Our issue tracker. OK, this is fixed, actually, yesterday. Anyway, this is the page, the original page on SourceForge. We get roughly 3,000 downloads every week. It's cool. And we have a forum in here where we answer questions to people, the students mainly. And this is the new documentation that we're pushing forward. So we have, based on Sphinx, and it's online. and it's multilingual. German? Wow, erste digital Schritte. And then it's based on Transifex, which is tightly integrated with GitHub, where we can push and pull translations from there. And this is crowd-sourced, so it's volunteers that are translating the tool for us. 1 minute. And I think that's it. So, yeah, it's flexible. It's quite powerful for what it is, for these 10 years or so the development, with very few people. It's quite nice. It's useful for beginners and professional users alike. And we are hoping to contribute more with other projects in order to make it even better. So the roadmap is quite bold, but we hope to get there someday, maybe with your help. And yeah, we are open to your help. And if you feel like it, join us on this journey. So, thank you.
Okay, we have 5 minutes for questions. I would like to ask the speaker to repeat the question. Right. The recording.
Okay.
So, yeah, questions?
So the Qucs netlist, how is it stored? It's probably text-based?
It's text-based. Yeah. It's a text-based.
And how is it support? Is there any support for Monte Carlo?
Okay, sorry. The question was if the netlist is text-based. Yes, it's a simple text-based. It's rather simple, actually. It's much simpler than Spice, for instance.
The XML?
Pardon?
Is it XML-based or just general flat text? Or
It's flat text.
no XML?
It's actually, you have to give all the parameters also. It's like full descripted in there. Yeah.
And how much support is there for Monte Carlo analysis?
No, none. It's roadmap. Yeah. Yeah, the question was Monte Carlo. It's just roadmap. Sure.
The model card you mentioned for the technology.
Yeah.
Is it your format or is it industry standard format?
So the model card for the compact models usually is just a list of parameters. It's quite easy to check, but it's usually based on Spice. So it's just a plus sign, the name of the parameter and the value that overrides the primitive. That's basically how it works. So we don't, usually simulators have include, then you include this file and everything works, but we don't have that on the simulator, so we are doing that on the GUI at the moment. So we have to create a new netlist entry, parse it, and process it in order to streamline the flow. Yeah.
Out of curiosity, I did see on your simulator, is there like any equation editing where, say I want to do a simulation and I want to figure out how much power my circuit can I calculate, is there like math programs that allow me, like help, give me the obvious example of PLC split, so I can figure out my average power dissipation for a given component in the simulation?
So it has a quite, so the question is if there are support for equations on processing the results. So let me switch back to English here, so it makes my life easier. It has some pre-process and post-process, but not on the loop. That's not implemented. So you can get, where is it? Mathematical functions. So all these functions you can drop into the schematic, and you can use to do stuff with either before the simulation runs or after the simulation runs. So yes, I think you can calculate the power. If you choose the right nodes and you write the right equations, it should give you the power. Yeah. So it's quite extensive actually. Yeah. So you see there is also RF and stuff here. Yeah. The question is whether we can do basic simulations, and the answer is yes. We have a library of digital components that it's okay-ish. You can kind of hand wire and do this. Yeah, for a small circuit it's quite okay. Yeah. Otherwise, I would recommend to go to Verilog or other more powerful. But for a small circuits and for studying and in teaching, it's quite nice. Yeah. And you can visualize the diagrams at the same time, so it's quite handy. Yeah.
How does the front end
it's okay. The question is how the front end talks to the back end. So the front end has its own schematic format, and then when you call the simulator, it spits out a netlist and calls the simulator. So it's separated. It's two. It's no, there is no back annotation at the moment. We just pick out. So the question is how we get the data back from the simulator. We tell the simulator to write a file, we read the file, and then we plot it. Okay, thank you.